Okay, so we were studying about the type of antenna systems, right? And we had looked on community antenna, and then can someone tell me which was the other one? Which was the other type of system that we studied? Yes, can I have some answers? Which was the other system that we were trying to discuss and we had discussed? So we were looking at master antenna television system, right? And it had its own pros and cons. And the community antenna is something where which we use for a wider audience, okay, rather than a very focused one as compared to our master antenna television system. Okay, so here you can see that this has distributed, okay, the filters based on the odd and even concept, and then you have a combiner, and then you have a cable distribution. Okay, so this works out well for a large number of users. Okay, so this was one such example which was taken up of Telesat, okay, from Canada in 1983. So here we were able to see that you know the antenna was about 26 feet, okay, which is about 8 meters, and it was operating in C band. Right. So today we will be looking into transmit and receive antenna earth stations. Okay. So here, uh, as we were discussing in the previous class, okay, systems need to transmit and receive. Okay. So which means this becomes a two-way communication, just like your duplex communication. Okay, where both transmitter and receiver can engage in communication at the same time, okay, simultaneously. So transmit receive stations provide both functions and are required for telecommunications traffic. Generally, okay, the network TV also. The basic elements for uh, redundant earth station, okay, is shown in the diagram. So here you can see that these are some of the basic elements, okay, that we use. And as you can see, these are all backup devices, right? So we have seen this concepts previously also, right? So these antennas, okay, will be very huge antennas, okay, just like how you can see here, very huge, which is actually uh, uh, performing the function of transmit and receive operation. Okay, right. So here we have even seen that the signal as it passes by, okay, if one set of the information is not if one set of these devices are not functioning, okay, then we will have another backup link to get the function up and running. Okay, so the block diagram is actually shown in clear here, okay, where you can see that, as I mentioned in the previous class, right, the up converters, then you have down converters, whatever happens here, okay, you have transmitting signal, and then it gets into the equipment for connection. Okay, and then once it gets into that, we will see that it is getting into the multiplexing. Okay, multiplex uh, operation. Okay, and also that you can see that once it gets into multiplexing, okay, it will get into modulators. Okay, then up converters, then you have combiner. Okay, power amplifiers, and then after that you have diplexer. Okay, diplexers are very important parameters. It's a very important device. Okay, where it is utilized, okay, for combining different signals, and it's a multi-purpose. Okay, it's a multi-purpose uh, device. Okay, next you can see that you have an LNA, low noise amplifier. Okay, because we have amplified things here, and then comes your divider. You have combiner and divider here, and then your down converters. Okay, or slowing down or getting it into lesser frequency, and then demodulators, then gets into the demultiplexer. Okay, demux, and then it gets into the equipment, and then for transmission. So this is your detailed diagram of transmit and receive earth station. Okay, right. So at the bottom of the diagram, the first block shows the interconnection equipment required between satellite and terrestrial network. So here, this diagram is what we are talking about. Okay, so here is where the connection happens. Okay, to the terrestrial network. So what is this connection to the terrestrial network? You would have seen that we are using TTNC, okay, which is nothing but your telemetry tracking and control, right, or command center, wherein all the information that needs to be passed to satellite, okay, it is routed via this center, and all the information that comes from the satellite gets into this system. Okay, so this equipment helps us in bridging both the satellite as well as the base stations. Okay, multiplexing is a method of grouping telephone channels. Okay, example, together usually basic groups of 12 without mutual interference. So if you can see here, okay, we had employed the odd and even concept, right? This kind is also employed sometimes, okay, in order to have efficient utilization of bandwidth and less noise. Okay, sometimes for tackling interference, we also use a guard band. Okay, guard bands are also employed, and interference can be in check with the help of guard band as well. Following along the transmit chain, the multiplexed signal is modulated onto a carrier wave and an intermediate frequency. Okay, it's about 70 megahertz is utilized. Uh, Parallel IF stages are required, one for each microwave carrier to be transmitted. Okay. So each microwave is being transmitted with the help of carrier, and we can have many such stages of intermediate frequency. Okay, so which means all these can start operating in parallel. Okay, after amplification at the 70 megahertz intermediate, yeah, intermediate frequency, the modulated signal is then up converted to required microwave carrier frequency. So that's the reason we normally go with the up conversion. Okay, so up conversion is done to make sure that uh, the frequency is blown up, and then we go into higher frequency range, because we have to start transmitting the signals, or it should be appropriate, okay, for us to go ahead with the transmission. Next, a number of carriers may be transmitted simultaneously, and although these are at different frequencies, they are generally specified by their nominal frequencies. For example, as 6 gigahertz or 14 gigahertz carriers. Okay, so this is going to be your upconverted frequency range. Okay, so generally in the form of 6 to 14 gigahertz. Now remember, from megahertz, okay, we are doing an upconversion and we are moving to another format, okay, which is in the range of gigahertz. So individual carriers may be multi-destination carriers. The same carrier is received at both places and designated traffic sorted out by filters at the receiving station. So you can have multiple signals, okay, arriving at the same destination. So in order to stop this, you can actually use filters wherein you can direct each signal to its own destination. After passing through the up converters, the carriers are combined. Okay, so that's when you see this combiner. Okay? So it gets into modulator, the IF stage. Okay, and then once it is up converted, it's actually into microwave carriers. The reason why we call it microwave carriers is because it's in a higher range, right? And then it gets into a section called combiner. And the resulting wideband signal is amplified. Okay, the reason why we call it as wideband is because after combining, okay, the spectrum is actually enhanced, and then the amplification happens. The wideband power signal is fed to antenna through a diplexer, which allows antenna to handle the transmit and receive signals simultaneously, right? So this is one important factor of a diplexer, okay, where it allows to transmit and receive signals, right? That is important. Okay, right. The station's antenna functions in both transmit and receive modes. We just do not want to have a single antenna which only receives information, and we do not want to have another antenna which sends information. Rather, we try to put them both together, okay, so that a single antenna can perform multiple functions. Because see, once we are designing a satellite, the weight um, ratio also comes into picture. Okay, we should try to make sure that these are very light in nature. So in such scenarios, okay, it's very helpful for us to design systems which can act for multi-purpose, okay, which can give us multi-purpose functionalities. The station's antenna functions in both the transmit and receive modes, but at different frequencies. Okay, so obviously we cannot have a single frequency in which both functions, but then we have to make sure that these are operating at different frequencies. In C-band, the nominal uplink or transmit frequency is 6 gigahertz. Okay, it's about 6 gigahertz, and the downlink or receive frequency is nominally about 4 gigahertz. Okay, so we have both 6 for the uplink, okay, and then we have 4 for the downlink. In the Ku band, the uplink frequency is nominally about 14 gigahertz, okay, and the downlink is about 12 gigahertz. Okay, so that's the reason. Okay, we most of the time use Ku band because it helps us operate at a higher frequency. Okay, right. Next, the high gain antennas are employed in both bands, which also means narrow antenna beams. A narrow beam is necessary to prevent interference between neighboring satellite links. Okay, so this is very much important. Okay, wherein it should be able to communicate properly uh, without the loss and also without the noise getting into our systems. In case of C-band, interference to and from terrestrial microwave links also must be avoided. So if in case the C-band is utilized, okay, we have to make sure that these noises from, see, because it's getting transmitted from the base station, right? So we have to make sure that even these signals are nullified. I mean the voice, the noise signals. Terrestrial microwaves links do not operate at Ku band frequencies. Okay, so that's the reason we use C type of signals, and then once we start transmitting, okay, then we can actually upconvert and accordingly we can um, use the gigahertz range, uh, and then we can just transmit. In receive branch, the right hand side of the figure, okay, um, where you can see these things here, okay, yeah. So this one you can probably logically divide as your for your transmitter transmitting section, okay, and this half can be thought of for your receiver section. Okay, in receive branch, the right hand side, the incoming wideband signal is amplified in an LNA and passed to a divider network which separates out the individual microwave carriers, just like how we have seen this in our OFDM, right? So the same type of technique is used here where it is separated into different subcarriers, right? These are each down converter to an IF band. Remember, now before IF band, it was actually in a very high frequency, probably in the range of gigahertz. Then now it has to get converted to the IF range, which means in terms of megahertz. And this needs to be passed on to the multiplex block where the multiplex signals are reformatted as required by the terrestrial network. So normally, if you can think of these terrestrial networks, frequency of operation is not as high as the microwave frequency range. Okay, so thereby, this needs to be down converted to an appropriate frequency wherein it adapts to systems that are involved, okay, in the base station. In general, the signal traffic flow on the receive side will differ from that on transmit side. Okay, so the signal traffic flow, we cannot say that the transmitter and receiver side will have both the same kind of traffic. Okay, so there can be chances that both can differ. Traffic can be broadly classified as heavy route, medium route, and thin route. Okay. So based on the traffic, based on the amount of information that is being passed from one end to the other. Okay. So these are the three divisions: medium, heavy, and thin. Okay. So if I would rate them in terms of numbers, then thin would be 1, medium would be 2, and heavy would be 3. Okay. So based on the density of the traffic, okay, these are classified into three categories. In thin route circuit or transponder channel, okay, normally we saw that we are using about 36 megahertz, and 4 megahertz, okay, can be used for guard band. Okay. uh, and a number of single carriers, each associated with its own voice circuit. This mode of operation is also called SEPC, single carrier per channel. Okay, so this is important. The antenna sizes, okay, now talking about how much big your antenna should be, right? So the size can range from about 3.6 meters, okay, for transportable stations, up to 30 meters. Okay, so from about 4 meters to about 30 meters for the main terminal. So we can see that here, uh, based on the requirement, okay, the antenna size also does change. A medium route circuit also provides multiple access, either on the basis of frequency division multiple access or time division multiple access. Multiplexed baseband signals being carried in either case. Okay. So we can see that if either we are using FDMA or TDMA, okay, in both the cases we will be using a multiplexed uh, baseband signal. Can someone tell me what is our FDMA? How how is it different from TDMA? Can you differentiate between the both? You can unmute and respond. Anisha, Anisha Devi, can you unmute? And can you tell me the difference between FDMA and TDMA? You can unmute and respond.
So TDMA is a time division multiple access,
Good.
and FDMA is for frequency division multiple access.
Okay. And how do they differ from each other? Pawan Kumar, would you like to answer that? How do they differ from each other? Pawan? Yes, or anybody else? You want to unmute and respond? A simple question which you have already seen, right, in your communications, the difference between FDMA and TDMA. Anybody else wants to answer? Okay. So here we basically, you know, think of using the frequency, okay, and in TDMA we use time slots, right? So time slots are given the importance, and in FDMA, okay, they are actually divided based on the frequency, okay. So both are altogether two different types of technologies, okay, and yeah. So Pranay has given us an answer saying TDMA is used in a different interval of time. Good. And Anisha has responded with the frequency range. Okay, the bandwidth of the FDMA. Okay, good. Thank you. Now, based on these ranges, okay, your sizes of antenna also does differ. Okay, as I told you, it can actually range from 30 meters to about 10 meters, or sometimes even 3 meters. Then in 6 by 4 gigahertz heavy route system, okay, each satellite channel having bandwidth of 36 megahertz is capable of carrying over 960 one-way voice circuits. Okay, so keep this in mind. It is able to carry about 960 one-way voice circuits. Okay, or a single uh, color analog TV signal with associated audio. Okay, so that comes under heavy route. Okay, so heavy route involves a lot of voice circuits, and if we have to compare, then it can be a color television, okay, along with the audio. In some systems, two analog TVs can be accommodated. Okay, so you can have a parallel connection between them, and thus it can be done. Thus, the transponder channel for heavy route circuit carries one large bandwidth signal, which may be TV or multiplexed telephony. Okay, the antenna diameter for heavy road circuit is at least about 30 meters. Okay, so most of the time what we do is we either think of the amount of signal that is being transmitted, and how much of frequency that needs to be occupied, and what is going to be the uplink frequency, the downlink frequency, and how much of IF, okay, the intermediate frequency that we need to take up, and also the size of the antennas. Okay, so these are some of the major important things that are considered. Ultimately, we would see what kind of system is it. Is it a medium root system, or is it a heavy root system, or is it a light root system? Okay, right. So as I was mentioning, this is one such example of a 32-meter antenna. Okay, so it's a very huge one. Okay, which was installed in California. Okay, and it's a standard A, okay, which is C band, 32 meters antenna. Can someone tell me why are we using C band here? We have a C band here, right? Why is it so that we are using a C band? Why can't we use KU band? Can we use a KU band here? Yeah, participants, can you all please respond? That's because we are using this in our ground stations. Okay, so our systems are very much adopted of using C-band. Okay, we do not use high frequency systems. Right? Only during transmission they get into the high frequency range. So it's a photograph of a 32-meter standard Earth station antenna. Okay, so these kind of antennas are actually used for communication with the satellite. It will be appreciated that for these large antennas, which may weigh in the order of 250 tons, a massive, okay, massive weighted uh, antennas, okay, which can weigh about 250 tons. The foundations must be very strong and stable. Why do you think so? The foundation should be strong and stable? Because of what? Because of the weight. Okay, so should make sure that they are they do not shake even though there is huge wind, because see, since the diameter is high, okay, so even if there is wind, okay, there are chances that there can be a little bit of wobbling. So we should make sure that the foundations, okay, are very deep, and then it's very strong, so that it can sustain any kind of harsh environment, any kind of rainfall or storm or wind. Okay, so it should be made sure that it is very strong and stable. Such large diameters automatically mean very narrow beams. Okay, so as the diameter increases, okay, the beam width also thus reduce, and therefore any movement which would deflect the beam must be avoided. So in some countries, yeah, we do have even this snow problems and the ice conditions. Okay, all these can actually hamper our communication system. So in order to counterattack these snow and ice, okay, you will even have systems which are built in with heaters, okay, which takes care of these snow and ice, so that automatically during those seasons, okay, the heaters automatically turns on, and these snow and ice just melts off, okay, so that it functions, okay, to its very best. Okay, so that's the importance of having an heater. Okay, so this is actually our last topic for our module. Okay, after which we'll be moving on to fifth module. Okay, right. So these are some more information, okay, that we will be looking into with regards to your transmit receive earth stations. Okay, and the surface heat of about 40 watts per feet square, okay, is also used. So the information with regards to heaters, okay, uh, is shown up here, okay, where we can try and understand, okay, all this information. Okay, so just have a look at it. Okay, so as I was mentioning, right, the antenna is uh, prone to ice and snow and all this stuff. So we need to have heaters, okay, heaters which can actually take care of the heat and which can actually melt off these ice and the snow. Okay, so the range is about 40 watts per feet square, and the main reflectors and sub-reflectors, and it's about 3000 watts for the azimuth beams. Although these antennas are used with geostationary satellites, some drift in satellite position and thus occur. Okay, so we have seen that this drift happens, right? Satellite drift. So we have seen this extensively in our previous modules, okay, as to how to tackle this and how um, TTNC comes into picture, right? Tackling these stuff, right? Um, This combined with very narrow beams of larger Earth station antennas means that some provision must be made for limited degree of tracking. Okay. So that also is another challenge. We should make sure that maximum signal, uh, maximum angle of tracking is also attained. Step adjustments in azimuth and elevation may be made under computer control to maximize the received signal. So all this is possible only through computerized tracking, computerized motion of the satellite, okay, and the antenna's position, and maximum signal can be sent as well as received, okay, with proper calibration. So all these are very much necessary while dealing with transmit and receive earth stations. So we will continue, okay, with the upcoming sections in our next lecture, and we'll try and understand as to what is still needed, okay, in order to attain a proper communication, okay, between the base station and the satellite.